Let's do one more example. Let's let T be a linear transformation that maps a vector space V to a vector space W, such that the set of all vectors V in the domain where the transformation on those vectors V is 0, that set is a plane in vector space V. Okay, and we also suppose that the dimension of V is equal to 3. We want to find the rank and the nullity of the transformation. All right. Now, the very first thing I want to point out is that this is not necessarily a matrix transformation. We know that V is a vector space. We know W is a vector space, but we don't know if it's like all of Rn or all of Rm. It could be subspaces of those or something like that, right? So we don't know that this is a matrix transformation. What do we know? Well, the dimension of V is equal to 3. So remember the rank nullity theorem? The rank of a transformation plus the nullity of a transformation should equal to n, where n is the dimension of the domain of the transformation. Okay? V is the domain of this transformation. The dimension of V is equal to 3. So in our particular case, this n is going to be equal to 3. Okay? Now, do we have enough information to find either the rank or the nullity? Notice, since we know the dimension of the domain, if I know the rank, then I can easily find the nullity, right? And vice versa. If I can find the nullity, then I can easily find the rank. So let's see what other information this problem tells me. It does have this weird statement here. The set of all vectors V, where the transformation on V equals 0 is a plane. Wait a second. Isn't that the kernel? The kernel of a transformation is equal to the set of all vectors in the domain such that the transformation on that vector is equal to 0. Okay, so this is talking about the kernel of the transformation. And it says that the kernel is a plane. For this problem, the kernel is a plane. Okay, well, what do we don't know about a plane? A plane is a two-dimensional vector space, right? It requires a basis of 2 vectors to span the plane. A minimum of 2 vectors. 2 vectors would be linearly independent. So what this is saying, if the kernel of T is a plane is a two-dimensional object, so that means the dimension of the kernel of T is equal to 2, because the plane has 2 dimensions. Okay? But the dimension of the kernel, that by definition is the nullity of the transformation T. So the nullity of T is equal to 2, and now we can really quickly see that the rank of T, in order to make this equation true, it must be 1. So we don't know a whole lot about this transformation, but we know that the rank of the transformation, based on what we were told, has to be 1. We know that the nullity of the transformation has to be 2. And we found that out using the rank nullity theorem.